Welcome, developers. Today, we're diving into an advanced agentic workflow, merging parallel feature branches. When you scale your productivity by running multiple Claude Code agents simultaneously, you eventually need to bring that code together safely. Let's learn how to consolidate this work seamlessly. Let's start with the big picture, multi-agent parallel development. What does this mean? It means instead of building features one after another, we deploy multiple instances of Claude Code to work on different tasks at the exact same time. Why do we do this? Because it dramatically scales our productivity, shifting us from a sequential, single-threaded bottleneck into a highly coordinated, parallel powerhouse. How does it work? You simply open multiple terminals or mix local and remote cloud agents and assign them independent tasks. But here is the critical deep dive. This only works if the tasks are truly isolated. If two agents try to edit the same file simultaneously in the same directory, chaos ensues. That's why we need a robust underlying architecture to keep these agents separated while they work. Look at this architecture diagram. You, the developer orchestrator, sit at the top. Instead of doing one thing sequentially, you dispatch 3 separate Claude Code instances. Agent 1 works on UI animations locally, Agent 2 updates the database locally, and a background agent handles a redesign in the cloud. They operate concurrently, multiplying your output by 3. But notice the distinct paths. They must remain separated during their execution phases to prevent file corruption. So, how do we keep these agents from stepping on each other's toes? The answer is Git work trees. What are they? Work trees allow you to have multiple working directories tied to one central repository, but each directory is checked out to a totally different branch. The basics are handled automatically by Claude Code. When you give an agent a parallel task, it spins up a new work tree. Why is this essential? Because it isolates the agent's file modifications. How do you see it? You'll notice new folders pop up in your project with randomly generated names like Vigilant Feastal or Zealous Jemison. For our deep dive, understand that these aren't just copied folders. They are cryptographically linked to your Git history but exist on separate branches, giving each agent a pristine, safe sandbox to manipulate code without ruining your main working directory. This visual demonstrates the Git work tree architecture. We have our main repository database on the left. Branching off it, we see our active work trees. Instead of constantly switching branches in one folder and wiping out uncommitted work, Git allows us to have parallel physical directories on our disk. Each Claude agent lives inside one of these isolated bubbles like Vigilant Feastal, tracking its own branch perfectly insulated from the others. Now we face the inevitable hurdle, consolidating parallel work. What is this challenge? It's the critical phase where we must merge our isolated agent branches back into our main project. The basics involve each agent finishing its task, committing the code, and pushing its specific worktree branch to the remote repository. Why is this difficult? Because while the agents worked independently, their code might interact in unforeseen ways. How do we start? We identify all our feature branches and our target integration branch. In our deep dive, we recognize that standard Git merges often fail here. If Agent A and Agent B both touched a global CSS file or shared routing logic, Git throws a merge conflict. Resolving this isn't just about deleting marker lines. It requires deep, semantic understanding of both features to ensure the final code actually runs without breaking the application. Take a look at this flow. We have feature A branch and feature B branch, both developed independently by our agents. When we try to funnel them both into the target branch, we hit a collision point, the dreaded merge conflict state in red. The system halts because it cannot mathematically determine which code should survive. It requires an intelligent entity, either a human or a reasoning AI, to untangle the overlapping logic. Instead of manually untangling code, we perform a brilliant maneuver, delegating the merge to Claude Code. What are we doing? We're assigning Claude the role of integration manager. The basics are incredibly simple. You open your terminal and prompt Claude with the names of the branches and tell it where they belong. Why do we trust Claude with this? Because it generated the code. It understands the semantic intent behind the changes. How do you trigger it? Just say, merge Vigilant Feastal and Zealous Jemison into our main branch. Now for the deep dive. Claude is incredibly safe about this. It won't recklessly smash code into your main branch. It automatically creates a temporary integration branch, something like hook hub merge. This gives us a safe staging area to consolidate the work without risking our production baseline. This sequence diagram shows Claude's brilliant merge strategy. You issue the merge command. Claude doesn't touch the target branch directly. Instead, it tells the Git repo to create a temporary integration branch. It merges branches successfully. Then, it attempts to merge branch B, but Git detects a conflict. Instead of failing, Claude catches the error and prepares a resolution plan to present to you, the developer. Let's dive into autonomous conflict resolution. What is it? It's Claude's ability to hit a Git merge conflict, analyze the competing code, and rewrite it seamlessly. The basics happen automatically. When Git halts and spits out those ugly conflict markers, Claude reads them. Why is this a game changer? Manual conflict resolution is tedious and highly error-prone. How does Claude handle it? It pauses and generates an explicit resolution plan outlining exactly which files it will fix. For our deep dive, observe how Claude uses its native edit tool to open the conflicted files. Because it understands the codebase, it doesn't just blindly pick ours or theirs. It semantically merges the logic, for instance, intelligently combining two separate CSS class additions into a unified style block, and then safely executes the merge commit. Observe the conflict resolution flow. Conflict markers are detected, prompting Claude to analyze the competing logic. It generates a resolution plan and uses the edit tool. The critical step is the yellow node, semantic blend. Rather than deleting one side, it intelligently combines the code, removes the markers, and automatically concludes the process with a Git commit. A clean merge isn't enough. We must enforce validating code integrity before pushing. What does this entail? It means spinning up your local development server and running your tests on the newly integrated branch. The basics are just running standard commands like npm run dev. Why is this absolutely critical? Because a successful Git merge only means the text doesn't conflict. It does not guarantee the application logic actually compiles or works. How do we enforce this? When Claude completes the merge and asks for permission to push the branch upstream, you hold off. Do not approve it yet. Our deep dive emphasizes the trust but verify mindset essential for agentic coding. You must manually check the UI or run the test suite to catch silent integration bugs like a missing import or overlapping variables that purely text-based merges miss entirely. This flowchart illustrates the mandatory validation gate. Claude prepares the final push, but we introduce a human-in-the-loop gate, highlighted in orange. The developer pauses the AI and manually runs the local development server. We hit a decision node. Do the tests pass? If no, we loop the errors back to Claude for fixing. If yes, we hit the green node and approve the push to remote. Never skip this gate. Let's look at a real-time use case, the hook hub consolidation. The scenario: a developer needs to merge 3 parallel agent streams into one codebase. In phase 1 of execution, we had 3 agents working simultaneously. Agent 1, named Vigilant Feastal, added complex UI animations locally. Agent 2, Zealous Jemison, updated our database JSON records. Agent 3 redesigned the hero section entirely remotely in the cloud. In phase 2, the developer simply prompts Claude to merge all of them into the main branch. The agentic action takes over. Claude creates the hook hub merge branch, immediately catches a CSS conflict between the animations and the new hero section, intelligently combines the styles, and finalizes the merge. The deep value here is profound. You can orchestrate complex updates across parallel branches, stepping back to act as an engineering manager overseeing a highly capable AI team, multiplying your output. Follow the hook hub consolidation journey. In the parallel work phase, our 3 agents' animations, database, and hero design are operating completely independently with high success. We transition to orchestration, where the developer issues the merge command and Claude creates the integration branch. In the final resolution phase, Git detects a CSS conflict, bringing a moment of friction, but Claude semantically fixes the styling, allowing the developer to verify and push the final code. Let's wrap up with our essential best practices for multi-agent merging. First, task scoping. Ensure parallel agents are assigned strictly independent files whenever possible. This minimizes merge conflicts from the start. Second, always verify that your agents have checked out the correct starting branch before they begin work. Third, test before pushing. Never blindly push a consolidated branch. Always spin up your local environment to verify the runtime logic. Finally, clean up your Git work trees after the merge is complete to keep your repository tidy. In conclusion, remember the golden rule: parallel agents work best on independent scopes. Start sequential and parallelize only when you know the tasks won't heavily overlap. By mastering these techniques, you become a true AI orchestrator. I invite all learners to like, subscribe, and visit quicktechie.com for premium certification prep, full ebooks, audiobooks, full-length training, and expert interview guides. Thank you. Our final mind map solidifies these best practices for parallel merge mastery. From the center, we branch out to scoping, emphasizing independent files to avoid shared states. We branch to preparation, verifying our base branch and utilizing work trees. We branch to validation, highlighting the absolute need for a local dev server to test logic. And finally, maintenance, reminding us to prune work trees and delete stale branches. Keep these principles in mind, and your multi-agent workflows will be unstoppable.